Hi! Week 4 of Crash Course Physics, and it's all about vectors. Not only are they a useful tool for describing velocity and acceleration in more than one dimension, but it is an essential tool. Many physical concepts, such as force, momentum, the electric and magnetic fields, are vectors. There's no other way around it. Vectors can represent simple displacements, like on a map, but also velocity and acceleration can be thought of and drawn as arrows. The arrow's length on the paper is a measure for the vector's magnitude using a certain scale. Now, the process of adding vectors has been explained. It makes sense when you think of displacements, and the result does not depend on the unit vectors along which you decompose the vectors. But what about, for example, velocity vectors? What does their addition mean, physically? The answer lies in the ball drop experiment. Indeed, why do both balls, one dropped, the other thrown horizontally, land at the same time? One way of answering this is to say that the gravitational acceleration points always downwards, never sideways, so it is natural to assume that it only affects the vertical coordinate of the ball, and in the same way for both balls. Another approach to the situation is to imagine the second ball has also been dropped, not thrown, but by someone moving himself. Maybe from the mast of a passing ship, as demonstrated in the movie Agora. As seen from the ship, the ball falls straight down the mast, if the ship is moving with constant velocity on quiet waters. From the bridge's point of view, the ball has the same constant horizontal velocity as the ship. Vertically, it behaves identically to the other ball. This is in fact one of the deepest principles of physics, the observation that the laws of physics, all laws of physics, are the same regardless of your frame of reference, as long as you stick to uniform linear motion among them. It's not the bus's speed that makes you spill your coffee, but the idiot who took its right of way. Such frames in uniform linear motion relative to a rest frame are called inertial frames. And the fact that the laws of physics don't care about the inertial frame you're doing your physics in is called the principle of relativity. Credits go to Galileo Galilei. Yes, the godfather of physics himself had a theory of relativity before it was cool. As a side note, the motion of a ball thrown horizontally, or at an angle, can also be understood by going back to derivatives. Acceleration is the derivative of velocity, even as vectors. So the velocity vector picks up, in a small time interval delta t, a change delta v equals a times delta t. So only its vertical component changes, while the x component stays the same. Similarly, the velocity vector at each instant, v, gives rise to a change in position, delta x equals v times delta t. Adding up those changes, we obtain the shape of the ball's path, a parabola.